is Hebert, and today I will present my paper about, and I will introduce you about the CSI for CPS. The CSI for CPS, it's a model to preserving the privacy and address to challenge and solution to implementation uh, of detection, threats and malicious scenarios and attacks in IoT and CPS, industrial components or uh, environments of technology. This model leverage federated learning to collaboratively training machine learning models in cyber-physical system environment. It invert accurate results while preserving data privacy, making particular beneficial in complex and dynamic CPS settings. This paper that I will present is the first validation of the CSI for CPS model using an IoT system framework. It highlights a new features, including real-time threat detection, consideration to false positives, and verification and validation of results. This model effectively detects intrusion in IoT networks and maintain the accuracy and the relevance as new data emerges. When we employ federation learning and the self-adaptive architecture of the CSI for CPS model, overcomes limitations of traditional centralized models. It sets a new standard for CPS cybersecurity, addressing data privacy concerns while delivering accurate and up-to-date results. So I will start presenting about this, and this is my outline and agenda for this presentation. First, I will present a context and motivation. I will planning provide a little background about federation learning. I will present a methodology and the framework proposed, the scenario and data sets. I will discuss about the results and the final considerations. So this chart is a little representative about the problematic that I will be explaining. Imagine this scenario: you walk into electronic store, and along of this row of the of your smartphone and the smart appliance, you come across a pellicular slide, a reseller for a file for your toaster, for example. At first glance, it may seem amusing or even absurd. After all, why would a toaster need a protection? But this seeming humor image serves as a stark reminder of the vulnerabilities and the risks we face in our increasing interconnected world. CPS and IoT devices have become ubiquitous in your home, office, and critical infrastructures. They bring us a convenience and efficiency and new possibilities. However, with this connectivity comes a significant challenge to ensure the security and the integrity of these systems. The motivation for protect the CPS and the IoT arises from the several factors. Firstly, these systems are interconnected, forming a complex web where a vulnerability in one device can potentially compromise the entire network. Attackers can exploit this weakness to gain unauthorized access, manipulated data, or disrupt the critical system. Secondly, this proliferation of the IoT device has outpaced to develop a robust security measures. Many manufacturers prioritize the function and time to market, often neglecting the crucial security consideration. As a result about this, we are faced with a vast array of devices with inherited vulnerabilities, making them attractive targets for malicious actors. In general, online safeguarding for CPS and IoT, it's a collective responsibility, and we have a big challenge here to keep it safe in this digital environment, and the federation learning can be addressing the solution for this challenge. So, what is federation learning? Federation learning distributes it's a distributed learning process across the multiple devices, preserving data privacy and ability, enabling collaboration. Instead of you sending the data to a central server to perform a learning algorithm of machine learning in traditional approach, it sends the device where local data is used to train model. You send only the parameters to construct and build the model for aggregation. The model are then aggregated to create a new global model, and the federation learning ensures the privacy when using this model building by the federation model. For this, federation learning use the feder average algorithms. This federal average use the stochastic gradient descendant to train and define the best parameters that define the best ways to minimize the function. This occurs with the calculation of the derivative function for each sample of the dataset. However, this process can use overhead in situations where the dataset has many samples. This is not a point that there is a possible contribution of the selection features, reduce the overhead. So uh, in this proposed model, I will show that we use the federation learning combined a traditional pipeline when used and take advantage of the selection feature to perform the federation learning. So the federation learning use three principal architectures. The first one is the horizontal that uses independent and identical distributed. Here I have the similar attributes in the dataset. The vertical is non-independent and identical distributed. I have the similar domains of the dataset, but the attributes are a little different. And the federation transfer learning, the datasets are different. So in this model, in this scenario, we use the horizontal architecture. So this is the principal approach that you use the architecture, and you use the principal server when I have for example, a two nodes, and I have the physical server system that collects the data in the environment, and I have a preprocessment of this data, and these data sets are processed, and we select the best features and ensure the data privacy and process the machine learning traditional pipeline. So this local model of machine learning send the best parameters for the federation learning process, and the federation learning process sending or the federation learning feedback the best parameters for the local node. So all nodes send or parameters and receive the feedback of the best parameters. So here we have a good cycle life of the retraining every time. So this is the CSI for CPS model in more components and details. The first part of the model is the responsible for data processing and the feature selection is the green part here, the bigger part. So we have the first part to receive the data and pre-processing the data, training, split the data set, and proceed this feature selection for three types, filter, wrapper, and embedded methods. We select the best attributes for this data set to reduce the filter and reduce the overhead about this process. So we perform the process of machine learning using the random forest algorithms or the federation algorithm used. We use the federation learning of the client to initialize the model, global model of the client and train this local federation client. The federation client export the best parameters for this another blue blue part is the federation learn server. Uh, this part of the process, the model parameter update the gradient of the descendant stochastic, and this model is aggregating obtain the new model, global model. This model global is export the feedback for the client. This process is repeat is similar for all the nodes, and here I have the cycle that occur in all the parts of uh, the model or the nodes that participate of this cycle. In the pink part, we have the online detection. So around that I have the detection mode or detection process, the actor or the specialist will try prediction the attack and the validation if this SQL is okay, it's working well, and I have false negative and positive. Of if I have false negative and false positive, this prediction are inserted again in this data set and this cycle of the reinforcement of this data set this machine learning process is repeated again and a new cycle is started again, and we have a virtual cycle of the reinforcement and the training again this model. So we have here a benefit of the federation learning because we don't share with the nodes the data. We share only the parameters, and I have the consensus of the best parameters. So all the time we provide for all the nodes the best parameters, and these data sets we can benefit about this online intrusion detection and validation for the actors in the online online and prediction and the false positive that are retrofit and the feedback that are input in the new data in the data set. That's why we train it all the time. So this is the framework implementation details. Here we have in the client node, we have a federation line component, and this federation component export the data for the federation line server and receive the federation average. This data, this how this environment was implemented with Google Collaboratory. The Collab is free cloud-based platform for developing your own machine learning using Python. That's a good option for machine learning. It's a normal consensus about this. Jupyter Notebook environment use the GPU and TPU resources. Its accessibility is popular among the data scientists and researchers and for machine learning practitioners. So I don't know have too much to speak about this. And this approach uses Keras, the high level neural network API writing in Python. It's very easy to implement this framework in this language. And here we have, if you have interest about this, uh, know more about how this is was implemented, you can I invite you to access this repository to check the code. So to implement this scenario is a big challenge because in true we don't have data set, no real or realistic data set to train this for uh, this text or I can go into the the, the hero scenario. Oh, please give me your data set to to test or let's go share your data. It's a problem. How I can try this model. It's a problem for any researcher. So we founded this realistic data set in the internet for another. It's a realistic data set that this data set have 7 million of data and 115 attributes. And this the IoT dataset is a result of meticulous research conducted in controlled laboratory environment. And this data set, the researchers capture the network traffic from IoT network release, and this and they are capture and analyze the security intrusion attempts, uh, attacks from DDoS, and that I'm the IoT device. This data set consists in 8 minor data sets and different equipments. This data set was infected by Gift and Mirai botnets that was very known in the industry. And this data set was multivariated. So to perform the experiment, the data set was divided in 4 nodes. Each node was divided in three and clustered in three steps. The first is used for the training, and the second for the test, and the another one for online detection. So the first node use this configuration for the first round, second round, third, and fourth round. And we simulate here, for example, 4 different organizations that use the federation learning to share your uh, experience or your detection model, but don't sharing your data specifically. Give the example of in the practice of the scenario simulation. The first scenario, I have here a little example of the online detection and the supervised process of updating data and the local data set and the machine learning process. Here we have, for example, 3 nodes or 3 companies that use the machine learning process, and we're in the first organization. We have the client node that the client node is connected to the federation learning server and share only the parameters. And this federation learning feedback for the organization the best parameters to the next round of the test. The second center of the federation learning is, sorry, the second scenario of the simulation, we don't have the federation learning. So it's just the only data set separated in the cluster, simulating the nodes or the companies separated, and use the isolated machine learning process. So uh, in resume, we compare this data to to images result. So the first, the I separate here the four more interesting scenarios to sharing. In the first example, when we observe the fourth round, the federation learning was better when you compare no federation learning for the last round. It's obviously because here probably in this round the node 1 and 2 probably in the moment that we're trying proceed the online detection receive a data that don't, don't have a pattern in your meaning process. So the similar occurring in another example here for the second example, when you have the down of the accuracy and here in the third scenario. So and here you have the similar comportment. In this study, we analyzed that this result that was obtained from the federation learning in this process in the different rounds. So when I show in this figures, we observe that no stabilized the patterns of in terms of accuracy. We have a different result all the time, but this lack of in these patterns is attributed of the dependence of the data arriving at each node. So wherever we note the accuracy remains stable in all phases when the federation learning process was employed. When used federation learning in the most part of the case, the the accuracy was very stabilized when in compare when you don't have the federation learning. Uh, it's very interesting when we observe that the time is it's obvious when you when we compare all the data with when we don't have for example here is different times when you use the complex data section or segregated data set. So in this experiment, we have observed that our model demonstrates a good occurrence to detect this cyber attack. It's important to know that the introduction of, of the federation learning and the feature select increased the response time by approximately 16% of average. It's important to mention this. This trade-off between accuracy and response time is a crucial factor to consider in implementation in the implementation of the SIC model. But looking ahead, there are potential avenues for the future exploration in this field. On promising approach in application of the vertical federation learning, which involve incorporating heterogeneous types of devices. So you have a good opportunity to use these another architectures of the federation learning. So putting these topics, we have a success of the self-adaptive model because we combine the feature selection and the federation learning was so it's a permission result and detect cyber attack scenario to that data set. We have a trade-off between accuracy and the response time. It's a problem because we have this average around 16%, but we have a potential for vertical federation learning here. When we think about the real world validation, it's possible think about don't use only data sets, use the internet. We're planning using in real industrial scenario than in Senai of São Paulo. So you have we have an industrial installation that we planning attack and use the pen test to simulate and perform attacks in the real scenario to collect and establish the normal network and attack 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 scenarios to train the machine learning in real scenarios. So here we have benefits for cybersecurity systems when you use the vertical federation learning. It's a we have a potential to enhance the security and the resilience of cybersecurity system. So the further direction is continued in this investigation into the feasibility and the practical of vertical federation. Just in this point that I mentioned before, using different equipments. So I think that this new architecture can be provide valuable insights for advancing the fields of the security. Oh, this project was partially supported by Advanced and the project Horizon and the Capizan Brazil, and they have a special thanks for the SES and SENAI for supported out. Thank you for